Now moving on to the backwards propagation part. This is where we're going to be going backwards and making changes to our neural network to the parameters such that we have minimum loss. So if you recall from the previous video, we used this formula: new parameters equals the old parameter minus learning rate times the slope or the derivative of loss with respect to the parameters. And we have 4 different parameters. In our case, we have W1, B1, W2, and B2. So in order to actually use this, we need to find these values. So we're going to have to find the derivative of loss with respect to each one of these parameters to use gradient descent. And we're going to do that with the help of backwards propagation. So that's just a little quick recap. We had the input layer here, we have our hidden layer here, then we had the output layer. We did a forward pass. We computed the outputs for the linear function and the activation function for both the hidden layer, the output layer. Then we applied a loss function. Now we're going to go backwards and compute the derivative of loss with respect to each one of these parameters. And then we're going to finally use this formula right here to update our parameters repeatedly until we have the optimal values or loss that is close to 0. Alright, so how are we going to compute the derivatives? I've already written down all of the equations here just to save time, and now we're going to be walking through each one of these. So to compute, first we're going to start with the second layer because we're going step by step. Just as we did the forward pass step by step, we computed the outputs for each layer one by one sequentially. The same way we're going to go backwards. We're going to be starting with the second layer. So first we're going to compute the derivative of loss with respect to W2 right here. And turns out we cannot actually directly compute the derivative of loss with respect to W2. We actually need to use something called the chain rule. So it goes something like this. So derivative of loss with respect to actually I've already written it down here. So derivative of loss with respect to W2 is equals to the derivative of loss with respect to Z2 times derivative of Z2 with respect to W2. Now, if you've done calculus before, this should seem familiar. This is something called the chain rule. So we can just cancel these out. And we're going to be left with derivative of loss with respect to W2. Now, we just need to find these two terms and multiply them. Well, I've already written down the formula for derivative loss with respect to Z2 here. It's A2 minus Y. And A2 is the output of the activation function which we got from the output layer. And Y corresponds to the actual values. So we won't be going into too much detail into the math here, just to save time. Otherwise it's going to be a very long video. I will leave a link in the description for behind all the math that goes behind finding this formula. So if you would like this, you can just go ahead and check it out. But for now, let's just proceed with this. So this is the derivative loss with respect to Z2, and we're going to be using this repeatedly. So I've just given this a variable name LZ2. So if you see LZ2, this means it's the derivative of loss with respect to Z2. All right. So we do that. We multiply this by derivative of Z2 with respect to W2, which is, if you look here, Z2 with respect to W2, that is going to be A1. So A1 times A1, and I put a small t up here. This means we need to do a transpose. And we're going to be multiplying this by 1 over m. M is the number of samples. And the reason why we're doing that, because we want the average values. Alright, so we have got W2, the derivative of loss with respect to W2. Then we can move on to the next one, b2. Same thing again, we're using the chain rule. So we do this loss, derivative of loss with respect to z2, which is again lz2. I've written it down here. You can just cancel these out. You can see that we'll be left with loss will be up here over b2, which is exactly what we want. And derivative of z2 with respect to b2, that is going to be, we can see it's going to be 1. It's going to be 1. So times 1, and again times 1 over m, because we need the average. And as for derivative of loss with respect to z1, we can see here. So we kind of just going backwards like this. You can see we're using the chain rule again. Loss, derivative of loss with respect to z2 times dz2 over a1. This is going to cancel these two out, and this is going to cancel these two out, and ultimately we'll be left with derivative of loss with respect to z1, which is exactly what we want. And you can see that derivative of loss with respect to z2, we already have that here. lz2, that's lz2, so I've written that down here. And then derivative of z2 with respect to a1, we can see that it is z2 with respect to a1, so this is going to get cancelled out. It's going to be w2. See, it's w2, and we put small t here, which is for transpose. And then a1, derivative of a1 with respect to z1. a1 with respect to z1, what is that? This is the value function, so we need to undo the value function. So I've just put down the value of z1 for now, because if you remember from the previous video when I first explained about the value, it looks something like this. So we have a graph which looks like this. So the derivative of value function really depends on the input. So if the input is a positive value, we're going to just have a straight line going up, and the gradient is going to be 1. And if it's a negative number, so we have just a straight line like this. If it's in this part, it's going to be 0. The gradient is going to be 0. So it just really depends on the input. I've just written down the value z1 for now, but we're going to actually implement it in the code in a few minutes. Okay, so I've labeled this as lz1. The derivative of loss with respect to z1, I've labeled it as lz1 because we're going to be needing this when we calculate the derivative for w1 and b1. So as you can see, we're using it here. So derivative of loss with respect to w1, that is loss with respect to w1. We use the chain rule again. So z1 cancels out. We're left with derivative of loss with respect to w1. So we have this term already over here, and we need to find this derivative of z1 with respect to w1. z1 with respect to w1, that is just going to be x, which I've written down here, and t is this means we're going to do transpose and times 1 over m to get the average. And then finally the final derivative of loss with respect to b1. Again, we just going to cancel this out. You can see we're left with derivative of loss with respect to b1. That is a chain rule. So we have this already, which is this right here, lz1. And the second one, the second term, derivative of z1 with respect to b1. z1 with respect to b1, that is just 1. That is going to be just 1. And then times 1 over m. Alright, so these are all of the derivatives. Now we can begin to write the code. Alright, so I'm going to define a function. I'm going to call it backward pass. It's going to take in a few inputs: x, y, a1, a2, w1, and w2. Alright, so the first thing we need to do is we need to calculate lz2. That's going to be a2 minus y. So A2 are the predicted values, and Y are Y are the actual values. So before doing this, we actually need to do an additional step, because if you recall, A2 is basically a two-dimensional array which stores the predicted values, and Y represents the labels or the actual values of the images. Now we cannot actually just subtract this from this. We need to convert Y to a different format, which is this right here. This is called one-hot encoding. So basically what we're going to do first is I'm going to define a function. I'm going to call it one-hot encoding. It's going to take in Y as input, and it's going to create a new array, and it's going to fill it with zeros, and we need to specify the shape, which is going to be the size of Y, and the number of columns is going to be the maximum element in the array plus 1. Alright, so let me just explain the step. Basically, we're going to create an array, and the number of rows is going to be the size, which is basically the size of Y. That is the number of samples that we have. The number of samples that we have, or how many images do we have. And the number of columns corresponds to the maximum element, meaning the largest value in this array plus 1. So the largest value is going to be 9. And we're going to add 1 to it, so it's going to be 10. So we have 10 rows, and the number of we have 10 columns, and the number of rows is the size. And then what we're going to do next is basically for each element here, we're going to create an entire new array, which is going to have 10 columns, and basically in the position for that element, we're going to fill 1. So for example, in the first row here, the actual value is 9. So in here, in the 9th position, we're going to assign 1. And similarly for the second element, which when it's 0, we're going to create an entire new row or entire new array, and all of the others other positions are going to be 0, and only in the 0th position we're going to assign a 1. Similarly for the third element, the third actual value is 1, so in the position of 1 we're going to assign 1, and all the others are going to be 0. So this is how we can convert our actual values into this kind of format, so we can carry out our calculations. So we're bringing it in the range of 1 and 0, so we can actually subtract it from this, which is our predicted values, which are also in the range of 1 and 0. Alright, so the way to do that is like this. So we're going to first we have created an array and we've filled it with zeros. Now we need to actually assign 1 to the correct positions. So basically, in the position of 9, for the first row, we need to assign a value of 1. So the way to do that is like this. We're going to do np of a range y.size. Basically, this is going to create an array from 1 or from 0 up till y.size, which is the number of samples that we have, which is again the number of rows, and and over here we're going to write the y, the y array, which is the samples, and we're going to assign it to 1. So basically what this is going to do, this is going to do this exact same step in the position for the for this element, for the actual value, it's going to assign it's going to assign a value of 1 in our array. So that's what this step is doing. Then we can do a transpose for this array, and then we can just return a transpose of this array. Alright, so then after we're done with after we've defined this function, we can just call this function one hot encoding. You can call it on y, and then this we can just update y. Alright, then after that, after we're done with LZ2, we can find the derivative for the W2, which is going to be LZ2 times A1 transpose. So I'm just going to call it W2 is going to be NP dot of LZ2 times A1 transpose times 1 over M. Oh, this is LW2. Alright. Then after that, we have the derivative for W2. For B2 is LZ1 times 1 over M. So LB2 is equals to NP dot sum. It's going to be NP dot sum of LZ2. It's going to take additional parameters. Axis is equals to 1, and keep dims is equals to true, and we're going to multiply it by 1 over M. Oh, and we didn't define M. M is going to be number of samples. Alright, so let me just explain this. So basically what we did is we took all of the values for the LZ2, we added them together, then we divided them. Basically we found the mean, because we need a single value for the bias, a single real value for the bias. Alright, then after B2, okay, another thing, I didn't explain this. So axis, we set the axis to 1 because we need to add the values vertically, and keep them true basically means that we're going to retain the original dimensions of the array. And Z1, the derivative of Z1 is equals to W2 transpose times LZ2. So LZ1 is equals to NP dot what was it? W2 times LZ2. So W2 dot transpose W2 transpose times LZ2. Then we multiplied it by the derivative of ReLU. So the derivative of ReLU, if you recall from the previous video, the ReLU function looks like this. So the derivative really depends on the input. So if our input is positive, meaning we're just gonna have we're gonna be on this side, so it's just gonna be a straight line. So the output of the gradient of this part, basically the straight line, is going to be 1 if it's on the positive side. If it's on the negative side, or meaning our input is negative, we're just going to have a straight line, straight horizontal line like this, which is going to have a gradient of 0. So we can just define a function for that, which I've already written over here. So dReLU is the derivative of ReLU. So this returns a Boolean expression. So if x is greater than 0, meaning it's positive, it's going to give back an output of 1. If it's negative, it's going to give back an output of 0, which is exactly what we want. So we can just call this function here. And we also need Z1. as input. So we're just going to add it here. All right, then after that we have the derivative of W1, which is LZ1 times X transpose. So we have LW1, which is NP dot of LZ1 and X transpose. We need to multiply it by 1 over m, it's the number of samples. Then we have the derivative of B1, which is simply LZ1. So derivative of B1 is equals to NP dot sum. Again, it's the same thing that we did here. So just paste that, but this time it's for LZ1. Alright, now that we're done, we can just return back all of the derivatives of the parameters. So we have LW1, we have LV2, and we have LW1, and we have LB1. So these are all of the derivatives for of the loss with respect to the parameters.